Okay, we will start today's class, and this week's topic, which is actually nothing less than the dawn of quantum mechanics. And specifically now, in the first part, we're going to go back to what we have previously discussed as the UV catastrophe. And today we're going to see what solved it, which was Planck's quantum oscillators. So, in that sense, as a primer, we can go back to where we were, right? We were in the description, the classical way of describing our system with some incoming frequency. We had the oscillating electron here, which perhaps is bound to some atom or something, or perhaps it was free. That was the Thomson limit. And then we got scattered radiation, okay? And we calculated the properties of that in various instances. And particularly we calculated also when it was close to resonance. And we got these very nice results for what we could call almost like a classical description of a spectral line, okay? We have already discussed the caveats that it comes with, right? One of them was that we predicted that all spectral lines should have the same strength, which of course we know experimentally is not true. We had in principle that in the line thing here, right, we had the classical cross-section times the profile function, which was the Lorentz profile function, nu 0, and the damping coefficient gamma, which in our classical example, right, was the classical one. We already hinted that, to be correct, and this is how we normally use it in descriptions in astrophysics, we actually just have to introduce some correction factors to the classical here. We introduce the oscillator strength, F, hence the name oscillator strength, as a correction factor to the strength of the spectral line. And when we have a Lorentz profile, which is often the case, for example, for the natural damping, then we need to do this by a general damping coefficient, which we then have to calculate or measure experimentally. It's not the same for all spectral lines as we predicted. Now, we also discussed the powerfulness of these spectral lines in terms of this Q value, right? Which we know was proportional then to this classical cross-section divided by nu 0 and then the Thomson cross-section, which was the limit of free electron scattering, right? Yeah? Or when this frequency, the incoming, is much, much greater than the resonant frequency, okay? And this, so to say, we know this is a frequency-integrated cross-section, so it doesn't have the same units as the Thomson, which is why we need this normalization constant. But this we knew it was on the order of 10 to the 7, 10 to the 8. And I think also in the exercise session, you actually showed that by doing our calculations, you came to this proportionality factor. So you actually showed that this was true. So the thing we considered then was that, okay, if we now shut the oscillator off, okay, at some time, then we had like a half lifetime of it, which was 1 over the damping coefficient, or measured in this, it's essentially the Q value here divided by a typical angular frequency now, right? And the order of magnitude here was that this was extremely short, okay? Now today we're going to now use this, but in another context. And that is in terms of the energy that is radiated away by this oscillator. So I actually did that. I thought we could just do that as just getting used to manipulating this. This is essentially repetition from your classical mechanics course because it works the same. It's just in this context that we set up the solution here, right? In this case that now we have shut off the driving. And we're interested in this lifetime. And then we could actually get a solution of this form, right? Cosine of omega 0t. But we know that the damping here, gamma, is very weak. Okay? Otherwise we would just damp away and wouldn't have an oscillation, right? So during one cycle we can, so to say, neglect how much it damps, particularly in these cases. So we could call this something like C effective, and then we could just take the time derivative here, right? C dot, which is going to be approximately then C dot effective, and then we just have to deal with that one. So it's just going to be negative 0 and then sine omega 0t. And why do I do that? Well, that's to set up the total energy of the oscillator. Okay? So the total energy of the oscillator then will be the kinetic plus the potential energy. The kinetic, in this case, 1/2 m c dot squared, okay? The potential energy of the oscillator is 1/2 m omega 0 squared c, where this is just your k constant. Yeah, that's the spring constant. It's another of the standard results. But if we now use this result in here, then we see that what we get is 1/2 m, right? Instead of the c dot, we could just substitute c f squared, right? Omega 0 squared, and then sine 0 squared omega t. And then we have the other part here where we already had the omega squared. This one is, of course, then the effective, as I called it, squared. And then we had the cosine there, right? My head just is, of course, that these are just 1. So, yeah, this is just then 1/2 m c squared effective omega 0 squared, right? And the C0 effective here is then just m0 omega 0 squared. Where was I going somewhere with this, or did I just do it? Yes, here. Because here I get another 2, right? So I get this one, okay? So you only get e to the minus omega t. That is that the energy actually decays with minus omega t, whereas the amplitude decays with 1/2 there. And that might have been a little bit of the confusion the last time. But the interesting thing for us today is that this just shows that we can set up the total energy area. If we calculate dV dt, it's just this one, right? So what comes out is just negative gamma, and then it's just this whole expression again, right? And that's just W, total energy. So the energy of the oscillator just decays according to this. And that's where I was going with this, because that's what we're going to use now. We remember this, so I can take it away, okay? Okay, now let's look at an interesting application. We're going to look at our whole realm, that is the black body radiation that we have had before, okay? And then we have our oscillators here, which are now in equilibrium. We can think about this in various ways, perhaps that it has reflective walls. And then the key point is that the energy that is radiated by this oscillator now, it cannot escape. It can only escape through like an infinitesimal hole here, which is the whole idea behind the black body radiation, right? So then it comes to an equilibrium, and classically then, when it reaches this equilibrium, the kinetic energy is going to be mv squared divided by 2, and then that is then 3 kT divided by 2. And this is a classical result, and we will actually deal with that when we do the Maxwell-Boltzmann distributions in the next chapter. I've tried my best to make the story linear. Here is where it fails a little bit, because we haven't actually gotten to this classical result yet, okay? So for now, we're going to just take it, yeah? This is it. We can look forward in the course notes, the book, or in the lectures. That's the classical result, that the kinetic energy is this, so that the total energy then is 2K, or in this case just 3 kT. Okay? Now, why is this interesting for us? Well, because we have done the whole oscillating systems, right? So we can actually say, all right, well, we know that these oscillators, they emit power. Okay, and now we're going to look at the frequency integrated power. Okay, and this frequency integrated power then, yeah, that is the integrated cross-section overall, and then it's the incoming flux. Remember that we had the cross-section as the relation between the emitted power and the incoming flux. So that was the Poynting vector flux, right? And then integrated overall frequencies if we're interested in the frequency dependent. But the Poynting vector flux in this limit, we know that we can just write as E nu times C d nu, where, mind the notation, this is now the radiation energy density in our standard radiative transfer language again. Okay? Remember we did this, that the flux there in this limit, vacuum limit, was just the energy density times the speed of light. Okay? So we have this integral here, right? But we know that in this case, the resonance that we were thinking about, these are classical oscillators, right? Remember that we calculated the typical width of the resonance, delta lambda, right? That was 1.2 times 10 to the 4 angstroms, okay? Which is tiny. And this means that to all purposes, over the line profile, this one, which is sort of the incoming black body radiation field, right? We know roughly how that varies. Varies much more slowly. So we can take that outside the integral, and then we see that this just becomes E nu 0 technically, if we take it at line center, right, as a typical value. C, and then this is just the integral, but we have done this for the classical. So this is just then sigma CL, what we did before. Okay, so now I have the power, but the power we know is energy per unit time, dV dt. So this is then just dV dt, okay? But we just had, for the oscillator, we know, right, that this was then just the damping coefficient, which we know in the classical limit is classical, times the total energy. The total energy we know for this equilibrium system must be this one. So here we have 3 kT omega classical equal to E nu C, like that. So if we now want to know the spectral distribution of this classical whole realm, it's just E nu equals 3 kT gamma CL divided by C. That's okay. But these ones we calculated the last time, so we go back to our notes and look at what were the expressions. Okay, so here we had 2 E squared 2 pi nu squared 3 MEC cubed, and for the classical frequency integrated cross section we had just this. Okay, well, then it's a plug and play exercise, right? All right, let's just do this so we can take a second to absorb this, because this is gonna come out in a very significant way, as long as we do it correctly. The likelihood might be small. And then we have this here, right? MEC, okay. Yeah, all right. So these go away. The masses cancel. We have a 4 there, we have an 8, then we have a 3, and we have 1 pi left. We have something like 8 pi. We have nu squared. Okay, how many e's? E squared, E squared. We have a kT, right? We have a C cubed left. I'm gonna it, yes. And this is E nu. But now it should ring a bell. Hopefully. What is this? What is this? Okay, energy density. In our radiative transfer language, we're going to write it here now. We can call this classical, yeah? 8 pi nu squared kT divided by C cubed. Okay, perhaps it starts to ring a bell if we do it like this. That, well, remember that E nu in our transfer language was 1 over C solid angle integral I nu the omega. Here we see that it's isotropic, so we can just take it out, right? So that's just 4 pi I nu divided by C. Okay, we're in the Hologram situation. So we actually already discussed the properties of this, that in this case, we could write this as 4 pi divided by c, b nu, where b nu was the Planck function. Yes? Now, b nu, we already discussed its properties, right? Was 2h nu cubed c squared 1 e h nu kt minus 1. That's the whole Planck function. But we said that, okay, what we call the Rayleigh-Jeans limit, that was the limit where h nu divided by kt was much, much smaller than 1. And that is just to Taylor expand this. This vanished, this goes up. See that the Planck's constant vanishes. So that's just 2 nu squared divided by c squared kt. Okay? So let's say that we have now E nu in the Rayleigh-Taylor. That's just then 4 pi c b nu Rayleigh-Taylor, which 8 pi nu squared kt divided by c, which is the same thing as we got from the classical oscillator. And this is, of course, no coincidence, because this was the result derived by classical physics at the time. And this was what led to people to say that, oh my God, there is something wrong here with classical physics. Because remember what happened, we already did this exercise when we just derived we discussed the properties. We didn't discuss any way where, we didn't motivate this in any way, right? We just discussed the various properties. But now we're in that part of the story. So the thing is that if you integrate this now, and now I will call it E classical, there. Then that's just the frequency integrated E nu classical, but you can just plug this in. This is nu squared. So it just means that we should have, for any given black body temperature, we should have an infinite amount of X-rays. Not an infinite amount, but an enormous amount. And we don't shine so much in X-rays, right? So for cool bodies, that's not true. Because here we just predict that this goes to infinity, always. And that is then what was called the ultraviolet catastrophe. Many people tried. There was no way around. We knew experimentally, of course, that this didn't happen. Okay? And that there was something very problematic here. So, what then happened in our story was that people had measured the curve. So we sort of knew, we have discussed the exponential cutoff of the Planck curve, right? We knew that that was there experimentally. So then Planck, he actually found empirically, he fitted a mathematical formula to this and found that, okay, this fits really nice. Yeah? And how did he obtain that classical formula? Well, we're going to just change the average energy of this oscillator from kT to some constant times their frequency divided by E h nu kt minus 1, where I now call the constant immediately h, because that's Planck's constant nowadays, right? So you can see that, again, this of course, has the correct limit in the classical sense. If we just, again, Taylor expand it in this limit, then we see that this expression there goes to kt, right? Hopefully we see that directly now from the one Taylor expansion that we must know in this course for 0 higher than x, much, much smaller than 1. Okay? So that had the right properties. And now, of course, I took away the board. But let's just redo the analysis with this expression for the mean kinetic energy instead of the kT. Then we would have this expression in U, 3 CL divided by sigma CL times C. But then instead of having kT here, we have h nu divided by E h nu kT minus 1, okay? And then in this case, we leave the steps out. This is algebra to come out with 8 pi h nu 3 c cubed E h nu divided by kT minus 1, which is 4 pi c B nu, where B nu now is what we know as Planck's complete function. So by doing this ansatz empirically, neat. Planck showed that we do away with the ultraviolet catastrophe. But of course, that was not complete story. Because he did more. He came up with a hypothesis why this could be the case. So here it goes. All right, what if the oscillators, instead of being able to have any given energy, could only have energies that were an integer multiple of this h nu factor? Okay, what would that be? And then we try to calculate the average energy of them from that. That is that the average energy then, well, that's the total of all of them divided by the total number, right? And here we have to use, again, Boltzmann's ansatz, that in this case, for these quantum oscillators, the probability to find one in a certain excited state was proportional to e to the minus the potential energy then of them. So we can call it like the energy divided by kT. This is again the Boltzmann statistical physics ansatz that we will use in the next chapter. And Planck assumed that this would hold for his quantum oscillator, but with the potential energy there. So let's see if we can do this now. All right, so then we have to sum up essentially all the energies, right, from some I equals to 0 to essentially infinity, and then we have to divide it by n, the numbers there. So if we look at the numbers first then, well, n0 is just going to be n0 then. Then n1 is going to be n0 e to the minus h nu divided by kT, because that's the only things that they're allowed to take. Okay? So we're going to call now this factor e to the minus h nu over kT for x. So this is just n0 x. Okay? Well, then n2 is just going to be n1, right, e to the minus h nu kt. So that's just then going to be n0 x squared. n3 then n0 x cubed, and so forth. So what about the energies then? Well, E0 here is going to be 0 because if the oscillator is not excited, there is no energy in it, potential energy in it. And E1, in this case, well, that's going to be N1, right, times h nu, the numbers, times then their energies. The numbers we had, right, so that's just then N0 h nu x. So then E2 is going to be the number in that state times the energies, but the energies could only take integer values, right? So that's 2h nu then. Okay, so that's going to be then, again, if we look at n2 here, it's an x squared, so that's going to be n0 h nu and then 2x squared. Okay, and then you can probably see how this is gonna work out such that the average energy is gonna be the total energy divided by the number total. That's gonna be then n0 h nu, and then we had like 0 plus x plus 2x squared plus 3x cubed plus and so forth, divided by n0 1 plus x squared and so forth. And if you carry out this sum with that, you will indeed see that it comes out as h nu divided by e to the h nu kt minus 1. And this is also then an exercise for you in the lecture notes. So what we have done now, except that we didn't really motivate this, Planck had to do that, is essentially the first ever quantum calculation done, one might phrase it as. And it showed that the ultraviolet catastrophe could be avoided by doing this empirical ansatz first, but then making this kind of weird assumption, which goes again classical physics, of that the energies could only take certain integer values here. But then it worked out, and you get the correct answer. And I actually think I wanted to just take a minute here to also discuss this in the view, because I think it reflects in a sort of way, it's an extremely profounding result, right? In the sense that this is what sparked the quantum mechanical revolution, if we call it that. And also the way it came about is interesting, because first was basically, okay, we know experimentally in astrophysics, that would be, we know observationally that there's something funny going on here. So we try around, we found some function that fits, and then afterwards we came up with a theoretical explanation of it. So this is what the Nobel Prize presentation read about this when Planck received this Nobel Prize. I think it was 1918 or 1919, I cannot remember exactly. Only a special case of the general radiation law, that was the state before. Yeah? Planck sought for, and in 1900 he found a mathematical formula for the latter, that's the general, which he derived theoretically later on, which is just what it is. And I also added Feynman's words about it, because, you know, if you can add Feynman's words, you should always add Feynman's words. That's a personal opinion of mine. Planck studied this curve. He first determined the answer empirically by fitting the observed curve with a nice function that fitted well. He had the right formula instead of kt, and then by fiddling around, he found a simple derivation for it, which involved a peculiar assumption. And of course, that was the beginning of the end of classical mechanics. So, you know, sometimes fiddling around with your equations can lead to pretty significant results.